Okay, in our final section of Chapter 5, we're going to be working at analyzing and comparing functions. And key vocabulary here is we're going to be talking about increasing and decreasing. And what these are talking about is you're talking about ranges in a graph. So if we had a graph, this here might be a cubic function, something like that. You can see that for this range here, we're increasing. And then for this range here, it's decreasing. And then for this range here, we've gone back to increasing again. And then if this was end behavior, that would continue out. If this was end behavior, that would continue out. So again, if I said a cubic function, from negative infinity to this point, the graph is increasing. From this point to this point, it's decreasing. And from this point to positive infinity, the graph is increasing. So that's the idea of increasing and decreasing. It's just measuring the trends in the graph. We're going to look at odd functions. Odd functions are symmetrical around the origin. And even functions are symmetrical around the y-axis. So let's go ahead and take a look at some of the things that we want to be able to do. Is we want to be able to compare two different functions when they've been given in different manners. So we'll finish this problem at the end, but you can see they've given me information for box 1. They give me an equation for the volume of box 1. So here's the equation. And then for box 2, they've given me a graph. Okay, so how do I compare an equation to a graph? So when we talk about comparing items that are functions that have been given to you in different forms, that's what we're talking about. They might have given me an equation. They might have given me an input-output table. And they might give me a graph. There are lots of different ways they could give me the information. How do I then compare two different functions when the way they've given it to me is different in each case? But first, let's take a look at what this means. I've already talked about this. Increasing over an interval means it rises from left to right, and decreasing over an interval means it falls from left to right. So if we take a look at something like this is sketching a graph given a verbal description. So the number of customers in a coffee shop, T hours after it opens. So now this is hours, the x-axis is hours, and the y-axis is number of customers. After it opens is as follows. It opens with no customers, it increases until mid-morning, decreases, then increases at lunch to its greatest number of customers for the day, and then slowly decreases until the shop closes in the late afternoon. So if I wanted to sketch that, this would be the 0 hour. So let's say that the shop opens at 6. Okay, and then maybe what we do is, let's see, 1, 2, 3, 4, 5, 6. That would be noon. 1, 2, 3, 4. Let's say that's the late afternoon. Let's go all the way to 5. Let's say that's 5. Right? So this is 5 p.m. So then we have 7, 8, 9, 10, noon, 1, 2, 3, 4. Oops, 5, 6 p.m. Okay, so if we wanted to sort of sketch the idea of this, at 6 we start with 0 customers, and in the late afternoon, let's say it's 5:30, so halfway between 5 and 6, that's where we close. We'll be back to 0 customers. And what happens is it opens with no customers and it increases until mid-morning. Let's say that's about 10. And then it decreases. And it increases at lunch to its greatest number of customers. So maybe up here by 1 we've sort of peaked. And then it slowly decreases until the shop closes in the later afternoon. So this is what this would kind of look like. So you can see that then over this interval it increases. And over this interval, it decreases. Over this interval, it increases. and over this interval, it decreases. So that's what we're talking about when you're looking at what does a graph do in the different intervals. Okay, so go ahead and give some practice on that. This was obviously not super specific. It didn't give a lot of details. So go ahead and do problem 4 to get some practice on doing this sort of thing, and then come on back. So now if we want to look at the average rate of change, what we're given here is we're given a lot of different x values. So in each case, this is x sub 1, and this would be x sub 2. X sub 1, x sub 2, x sub 1, x sub 2, x sub 1, x sub 2. So we were given 1, 2, 3, 4 different pairs of x values. And if I want to examine the intervals, what I want to do is I want to figure out the average. So that's going to be x1 minus x2. That's going to be the change. I'm sorry, x2 minus x1. That's going to be the change, and the average change would be dividing it by 2. Okay, so if I want to go ahead and do that for the first pair, I would sub in these x values. So first I'd do 3 to the negative 3 plus 4. Remember, I subbed in x2. And then 3 to the negative 4 plus 4. All divided by 2. So negative 3 plus 1 is 1. So that's going to be 3. Negative 4 plus 4 is 0. So 3 to the 0 power is 1. So 3 minus 1 divided by 2 is 2 divided by 2, which is 1. That's the average rate of change. Okay, if we go ahead and we go back through, now you notice they've given me items that repeat, so I don't have to do this one again, right? So if I'm going to do x sub 2, I'll have 3 to the negative 2 plus 4 minus the same value, but it's 3 to the negative 3 plus 4. I've already calculated that, right? So that's this number here, so it'd be minus 3. Negative 2 plus 4 is 2. 3 squared is 9. 9 minus 3 is 6. 6 divided by 2 is 3. Okay, so now when I do the next one, I'll have 3 to the negative 1 plus 4. That's new. Minus this item, negative 2 plus 4, which was 9 over 2. This would be 3 to the third, which is 27. 27 minus 9 over 2 is 18 divided by 2. Average rate of change is 9. And my final one will be 3 to the 0 plus 4 minus 27, all divided by 2. So 3 to the 4th power is 81. 81 minus 27 divided by 2. So that's going to be 54 divided by 2, which would be 27. Okay, so that's how you go about doing it, right? You'll notice that in this particular case, because this number and that number were the same, that means that this number and this number were the same, right? And so on. So you'll see that this number became that number, this number became that number. So you don't have to redo the calculations if you've already done them once, right? Save you a little time. Go ahead and practice that. Calculate average rate of change here doing problem 8, and then come on back. So when we talk about odd and even functions, now you'll notice also that this is probably a 4th degree function. It has 3 terms. The end behavior, both ends do the same things. Leading coefficient was positive. They both go up. So this is probably a 4th degree equation. This is probably a 3rd degree equation. That has to do with why they're called even or odd, but they have specific characteristics. Right? An even function is symmetrical around the x-axis, or the y-axis, excuse me, the y-axis. An even function is symmetrical around the y-axis. Okay, so you'll notice that the opposite of x, y, is going to be the same as x, y. So when I have opposites, this is what's important to think about. In an even function, when I have opposite inputs, they result in the same output. Okay? Opposite inputs result in the same output. That's what happens when every time I take the variable to a power, it's going to the even power because it eliminates the idea of positive and negative. In an odd function, when I take opposite inputs, I get opposite outputs. Okay, so this is symmetrical around the origin. Now it's important to remember that not every, even though I said this looks like a fourth degree equation and this looks like a third degree equation, not every fourth degree equation is an even function, and not every third degree equation is an odd function. They won't all automatically follow these rules. This is what you need to look at. You need to look at what happens when I put in opposites. What do I get? Okay, so that's the way to test. Odd functions are symmetrical around the origin. An even function is symmetrical around the y-axis. Okay, that's what you need to check for. All right, so go ahead and practice identifying even and odd functions. Let's take a look at how that looks. So if I want to check these, right, if I do x, let's do 1 and -1, 2 and -2. Right? That'll give me a sense of what's going on. So when I have 12 divided by 1 is 12. 12 divided by -1 is -12. 12 divided by 2 is 6. -2 divided by, 12 divided by -2 is -6. So you see, this would be an odd function. When I put in opposites, 1 and -1, I get opposites for outputs. Right, now let's test this other item. And you can see now, this is important to help you identify these things. You can see now that every power of the variable is an even power. Okay, I can tell you now what's going to happen in the output table, because it doesn't matter whether I put a positive or negative value into this. Anytime I take a negative number to an even power, it's going to become a positive number. So, but let's do the same thing. -1 and 1, -2 and 2. -1 to the 6th power is 1, times 5 is 5. -1 to the 4th power is 1, times 9 is 9. And -1 squared is 1. So this is 15. 1 to the 6th power is 1, times 5 is 5. Right? You can see that this isn't going to change. 1 to the 4th power is 1, times 9. And 1 squared is 1, so it's 15. And the same is going to happen when I put in 2. 2 to the 6th power is 4, 8, 16. 2 to the 6th power is 64, times 5 is 320. -2 to the 4th power is 16, times 9. 90 and 54 is 144. And then -2 to the 2nd power is 4. And you can see that when I plug 2 in, I'm going to get the 64 and the 16 and the 4, just like I did here. That's what it looks like when it's an even function. So 320 and 144 is 564, 568. Right? So this is even. Okay, what's important is that they're the exact same values. Okay, what's important here is that they are opposites. Okay, so go ahead and practice identifying even and odd functions. Do problems 15 through 17. Come on back and we'll finish out the lecture. So if I want to compare my two equations, I kind of have two choices. I can either try to generate the equation of box 2 from the graph, or I can graph box 1 from its equation. Well, I think graphing box 1 from its equation is first going to be easier, and second, it's going to provide me with a lot more information than if I did it the other way around. I could do this by hand. That would be fine. I can see that I'm going to have intercepts of, right, if I set these to be equal to 0, right, if x is equal to 0, if 8 minus 2x is equal to 0, and if 3 minus 2x is equal to 0, then I know that I'm going to have an intercept at 0. I'm going to have an intercept at, let's see, 8 equals 2x, x equals 4, at 4, 1, 2, 3, right, 4 way out here. And then this would be 3/2, so 1.5, there's an intercept there. Okay, what's important to remember is this is a third degree function, so this is going to increase in this up to here, up to some sort of maximal, and it's going to decrease to here, and it's going to come back up. You'll notice I'm not going to care about, right, what are we graphing? We're graphing volume of a box. Down here, my volume is a negative number. I'm not going to be worried about that, right? I won't be thinking about that. So I know I've got these points, but what I want to find is I want to find my maximum up here. Okay, so if I were going to do this by hand, I might try plugging in, I could try doing an input-output table, 1. So if I have 1 times 8 minus 2, 1 times 6, times 3 minus 2 times 1, that would be 6. So I know at 1, I'll be at 6. Okay, but I don't really know if that's the maximum. In fact, I rather suspect that it's not. I would expect it to be somewhere here in halfway between 0 and 1.5. So this is a case where I might want to go ahead, and the fastest thing would be to plug it into a graphing calculator. So I went ahead and plugged it into a graphing calculator, and I used the trace function to find that my maximum point was at 0.64. And that maximum is at 7.4. So at 0.64, right, this is 0.75, 0.64 would be right around in here. I'd be at 7.4, so right about there. So that helped me find the maximum. If I go ahead and put some more values in, at 0, I'm at 0. At 2, I'm at -8, so that's kind of unhelpful, but you can see that I've got a graph that's going to look something like this. All right, by graphing it with the other graph, it allows me then to make a comparison. You can see that box 2 has, in general, has a greater volume for the given sizes. Okay, so when you look at the x-intercepts, right, where I get back to 0 in volume, right, is smaller here, bigger here, right? The volume for box 2 is shown on the graph, so box 2 has a greater volume in general. And you look at the maximums, you can see that box 2 has a maximum volume of about 8.5, whereas I have a maximum volume of about a little less than 7.5. Okay, so the key here is in trying to put them both into the same form. And because I had a graph and it's sort of continuous data, graphing them both is going to be much easier. I wouldn't learn near as much by looking at 2 equations. And I wouldn't learn that much necessarily from looking at 2 input-output tables if I just picked integers. If I just pick integers here, I have 1 is 6 and I have 2 is -8. So it's very unhelpful in terms of trying to find the important parts of the graph. All right, so that's just part of what you want to do. Typically, if you want to compare 2 things that are given to you in different representations, the best method is to take and put them into the same representation to make an accurate comparison. Okay, so you could compare equations, you could compare input-output tables, you could compare graphs. In this case, comparing the graphs gives you much richer and more detailed information.